We now continue with the section 2.8 notes with example 7, which is an application of a function composition. The radius r in meters of a circular oil slick as a function of time t in hours that has elapsed since an oil spill occurred is given by r of t equals 50 times the square root of t. If the area A of the slick is A of r equals pi r squared, just the formula for the area of a circle, find the function A composed with r and interpret its meaning. So first of all, let's write down by definition what A composed with r would look like. Notice r is going to be the inner function. R is a function of t. So A composed with r should also be a function of t. It should be defined as A of r of t. Now working from the inside out, that would be A of 50 times the square root of t. And then 50 square root of t would replace the r within the function A of r. So this would be understood as pi r squared, but r is 50 times the square root of t, so that gets squared. Now simplifying, 50 squared is 2500. Square root of t squared can just be written as t. So our function becomes 2500 times pi times t. This actually is a linear function and is showing us that the area of the slick is increasing at a constant rate. That constant rate is 2500 times pi, a little bit more than 7500 square meters per hour. So in terms of the meaning of this composite function, the composite function allows us to relate the area of the slick directly to the amount of time that's elapsed since the oil spill occurred, without computing the radius of the slick first. So A composed with r gives the area of the slick as a function of time. Finally, moving on to example 8, we'll look at a graphical interpretation of various combinations of functions. Both, well, we're going to look at a difference of functions and then a couple of compositions. For the functions f and g graphed below, find in A f minus g of 0. Now we don't have equations or formulas given for f and g, so we have to just rely strictly on the graphs. But it's actually not too difficult as long as you know what to look for. F minus g of 0. Remember that f minus g of x equals f of x minus g of x for any x in the domain of the function f minus g. So here x is equal to 0. F minus g of 0 therefore would be f of 0 minus g of 0. So the question then is, what's f of 0 and what's g of 0? Well, x is 0. So on our graph that's here, f of 0 would just be the y-coordinate associated with x equals 0 from the graph of f. And we see that the point 0, 2 is on the graph of f. That means f of 0 equals 2. Similarly, g of 0 is the y-coordinate corresponding again with x equal to 0, but using the graph of g. In this case, we can see that that y-coordinate is negative 1. So g of 0 is negative 1, and 2 minus negative 1 is 3. So f minus g of 0 equals 3, just referring to the graphs of f and g as shown. Part B, g composed with f of 3. Well, this is defined as g of f of 3. G of f of 3. Now, here we want to work from the inside out. Let me erase, if I can. There we go. Let me erase what I did previously. What is f of 3? Well, find x equals 3. 3 is your x. Now find the point on the graph of f and read the y-coordinate of that point. The y-coordinate of that point is the function value. So function values always correspond to y-coordinates of points on the graph of the function. So the y-coordinate is 2. So this would be equivalent to g of 2. All right, so now what is g of 2? Well, find x equals 2. Notice that the y from the graph of f becomes the x for the graph of g. So what is g of 2? It's the y-coordinate at this point. And it's not completely obvious what that is, but it would appear that it must be 1/2. That would be the most likely value. So 1/2. And that gives us g composed with f of 3. Finally, the value of f composed with f of 1. Here we're going to work strictly with the graph of f. F composed with f would be f of 1. Well, what is f of 1? Find x equals 1. Find the point on the graph of f corresponding to x equals 1. What's the y-coordinate? Looks like it would be 3. So this is f of 3. All right, what is f of 3? I guess we have done that one previously, but here's x equals 3. Look at this point. We see that the y-coordinate would be 2. So f of 3 is equal to 2. Therefore, f composed with f of 1 is equal to 2. So if you understand what to look for on the graph, when we evaluate f of x for a given x using a graph, the x comes from the x-axis, the value on the x-axis. The f of x is the y-coordinate of the point associated with that value of x. So remember that f of x is a y-coordinate when it comes to interpreting it as a point on the graph. That concludes the notes for section 2.8.